Hi there! Welcome to the 42nd episode of the Synth project, where we are building a synth together. It is time to add a new element to the MIDI module that will help in running tests with a prototype connected directly to the actual synth rack and a MIDI keyboard. The capability to locally generate a plus 9V voltage from the plus 12V provided on the synth power rail. In addition to that, we will add a new reset button that will find its place on the module front panel to make possible the reset of the Arduino DUE board even though the Arduino won't be directly reachable. And finally, we will add what I call navigation buttons that will be used in a future version of the MIDI module. The intent for these buttons is to provide later on new features without the need to make hardware changes to the module itself, thanks to the programming USB connector that will also be extended to the front panel. Let's dive immediately in all these things we have to cover. First thing first, I have added to the schematic a pin header for the connection to the synth power rails, here shown as header H11. This will bring the power supply from the rack to the MIDI module. The possibility to use the rack power supply will allow us to bring the prototype to the synth without dealing with all those cables we used so far to power it up. To complete the powering needs of the prototype, we have also a simple unit that will convert the plus 12V to plus 9V, drawn here on the bottom of the schematic. The unit is very simple. It is built around an LM7809 voltage regulator, along with a few more components. We have a 330 nF capacitor, named C8, at the input of the regulator, to filter out any possible high-frequency interference going in or out the regulator. It comes useful to avoid the injection of the Arduino high clock frequencies back into the other circuits of the synth. Capacitor C7 does basically the same thing, but on the side of the regulator output. Capacitor C9 instead is used to level possible ripples of the output voltage induced by sudden changes in the load. And finally, diodes D4 and D5 will get into action when the synth is powered off, in case the input voltage drops faster than the output voltage, due to the presence of C9, and also to avoid any possible issue with the circuitry of the Arduino and the other circuits directly connected to it. These two diodes are actually suggested in the LM7809 datasheet to prevent the disruption of the regulator during power-offs. The plus 9V produced by this circuit is injected directly to the V-in pin on the Arduino DUE. From that voltage, the Arduino will take care of generating all the other voltages internally required, exactly as if the plus 9V was inserted through the cylindrical connector on the side of the Arduino board. The next element added to the schematic is this connector P6, which on one side is attached to the reset pin of the Arduino, and on the other side will go to a normally open push button. When the button is pushed, it will bring the reset pin to ground, causing therefore the immediate reset of the Arduino board and all the other circuits attached to it, in particular the USB host shield and the 1602A LCD. And finally, the last block added to the schematic is the one of the navigation buttons. These are 5 buttons which will be labeled as up, down, left, right and enter, that will not be used for the current design, but will be there available for future software version of the MIDI module, that will use them for making specific selections to customize the module for specific situations. These 5 buttons on the panel will be electrically connected to the headers from P1 to P5, thanks to the voltage dividers made with resistors R17, R18, R20, R21 and R22. Whenever we will push one of these buttons, a different voltage will be applied to the analog pin A11. Based on the voltage, the Arduino will recognize which button has been pushed and will act accordingly. I opted for this solution because it will allow me to use a specialized library for the Arduino that will also take care of handling the bouncing of the buttons, therefore avoiding false inputs. To see more clearly how this circuit works, Look at this simplification of this schematic section. It is easy to see that every time a button is pushed, a different voltage divider is connected to the 3.3 volt power supply, and therefore a different voltage is applied to pin A11. Let's now take a look at the software change since last episode. From the version log, which I try to keep always updated to retain a history of all my changes, we can see that the modifications are solidly related to the handling of the navigation push buttons. And in fact, these changes are just a skeleton to make it easier in the future to keep adding new features to the MIDI module, assuming, of course, that I will not need any further hardware change. The first new line of code is about the inclusion of the analog buttons header, which provides us with everything we need to interact with a library of the same name. I decided to use this library because it provides a solid way to deal with buttons of any sort. Among other things, this library takes care of handling the contact bouncing and also makes possible the use of several buttons on the same analog pin, thus reducing the clutter due to all the wires lying around. The next few lines are all about the interactions with this new library. We start from the definition of a bunch of constants, from the first defining the analog pin used for all the buttons, to the tolerance of the codes for each button, to the codes themselves. Yeah, I know, you are already thinking about these codes. What are they? Why do we need them? And what complications they will add? Okay, let's pause a bit the software description and let's clarify what these codes are and how they are used. We already said that each of these buttons, when pushed, apply a different voltage to pin A11. This pin is internally connected to an analog-to-digital converter, or ADC, so the voltage will be immediately converted to a number going from 0 to 1023, according to the default resolution of the analog inputs. The codes we are talking about are just these numbers coming out of the ADC. So basically, every time we push one of these buttons, we obtain one of these codes from the ADC on pin A11. You can see from the table how I was able to associate the voltage values to the ADC readings. Basically, we calculate the output of the voltage divider associated with a specific button, then we convert the voltage to the value obtained by the ADC, which depends on the max value from the ADC itself, 1023, and the max voltage value, 3.3 volt. The margins of the rightmost column are merely the difference between the next ADC number and the one in the same column divided by 2. Therefore, they represent the distance of the ADC numbers from each other divided by 2. So they basically represent the maximum admissible deviation of each of the ADC output values that will not interfere with the other values. These numbers are important because the resistors used in the voltage dividers have tolerances, and in addition they may slightly change their value at the change of the temperature in a synth case. Having a range of values rather than a single specific value for each button makes certain that we can identify all of them in any situation. So, back to our software, all these constants represent the output values of the ADC for each of the navigation buttons. And of course, there is also the value of the margin, which is smaller than the smaller number we have calculated. The first constant instead identifies the specific analog input we are using. On line 33, we have the allocation of the object that will handle all the navigation buttons. Whenever this object identifies that a button has been pushed, it will call a callback function specific for that particular button. It is this function that will do all the work needed when the particular button is used. The lines from 35 to 39 declare all the callback functions that will be used by the push buttons object, and the lines from 41 to 45 allocate each button object along with the name of its callback function. How easy is that? Next changes start on line 109, where all the callback functions are defined. Right now, since we don't have yet a specific use for them, the only thing they do is to print on the serial monitor and on the display the name of the button that has been pushed. This of course is temporary code and will be replaced as soon as we will have a use for these buttons in a future software version for the MIDI module. The last two changes are in the setup and loop functions on the Arduino code. In the setup function we add each of the button objects to the object that will handle them, which is the push button object. And finally, in the loop function, we call the method check of the push button object that polls all the navigation buttons. This method will take care of calling the most appropriate callback function every time a button is pushed. There is one more function call that has been added to the loop function, but that is currently commented out, and it is also defined later on starting on line 363. This function is only there to double-check the numbers generated by the ADC, to make sure they coincide with those we have calculated. I will uncomment the function call on line 360 just once to verify these numbers, and eventually make the necessary corrections to the corresponding constants that we have previously defined. Then the function will be commented out one last time, and it will never be used again. And now let's take a look at the changes on the prototype. They are essentially on this breadboard and in this other one. On this first breadboard we'll have the circuit that converts the plus 12 volt from the power rails to the plus 9 volt that the Arduino DUE uses to generate all the other voltages it needs to power the USB host shield, the two logical levels converters and the LCD. Still on the same board, we have one push button that will replicate the reset of the Arduino on the MIDI module front panel. The button is connected to the Arduino through this yellow wire. The breadboard on the left hosts instead the 5 navigation buttons with the associated circuitry. We have the up, down, left, right and enter buttons with the corresponding resistors making the voltage dividers. Because of the new 9V power supply, there is no need anymore to keep around all those power cables, starting with the one that was powering the Arduino DUE. Now we just need this board that provides a plus 12 and minus 12V coming either from the bench power supply or from the Synth power rails. This is the power supply I will be using here on the benchtop, which provides me, among other things, a stable plus 12V and minus 12V with respect to ground. Turning it on now, and the system initializes immediately and we can see the initialization completed message. And touching the pad of the Akai LPD8, we can confirm that we receive and decode the MIDI messages from the USB cable. Now, just to double check, let's measure the plus 9V coming from the regulator built on the breadboard to the right. For that, I will use this multimeter, which I am now connecting to ground and to the plus 9V output. And the multimeter shows 9.18V, which is perfect for our needs. Let's check now the reset button. As soon as I push it, we should see the Arduino going through a reset and a new initialization, and the LCD should report that. Let me zoom in, pushing the button, and here are the initialization messages on the LCD. The last thing we need to do now is to test the navigation buttons, and for that we need to first upload the new code on the Arduino DUE. So first let's connect the USB cable from the Arduino to the laptop. The Arduino IDE tells me immediately that the connection is done. Now let's compile the code and download it. Yeah, and of course there is a compilation error, and that's because I built this code on another computer, while in this one I did not previously install the analog buttons library. So let's install the library. And now let's build again. This time the build is successful, but since I also want to check that the button codes are correctly calculated, I will have to enable the function push button configuration. Now let's build again, and let's upload the code to the Arduino DUE. And we can see that the initialization has been already completed, and so we can start testing the buttons. For that, we need to open the serial monitor and look for the numbers that come out when I push the buttons. Pushing the up button now, and the number that comes out is around 354, 355. Pushing now the down button, and the number is now 555. Now the left button, which gives us 692. Then the right button, and the number is 853. And finally the Enter button, which provides the number 932. Let's now check the original code and let's see if the numbers match what we have initially put. And yes, we have to make a few slight changes, although the margin would cover for these differences. So let's change the number for the up button to 354, and then 566 for the down button, 692 for the left button, 853 for the right button, and finally 932 for the Enter button. So it looks like my calculations were very close. These slight changes between my calculations and the actual numbers were most probably due to the tolerances of the resistors used for the voltage dividers. Now, as long as the resistors used for the dividers are of 1% tolerance, I believe there won't be any need to make any future change to these numbers, and you can use these same numbers as well if you end up building this module. Furthermore, to stay on the safe side, I'm going to increase the margin a little bit, from 35 to 40. We can now save the changes, build again, and re-upload the code. And now we can go back to the prototype where we can see that the initialization has been already completed and test the button to see if the correct message comes up on the display. The up button. That's good. The down button, well, which doesn't seem to work. Oh, now it works. I think this is because I forgot to disable the push button configuration function. So let me go back to the code again. I'm now commenting out the function call, rebuilding, and uploading again. Let's rerun the test now. Up button is OK. Down button is OK. Left button is also OK, as well as the right button. And finally the Enter button, which is also OK. Let's now make sure that everything else is still working using the LPD8. And yes, everything seems to work fine. Very good. So far we have added a couple of important functionalities, the 9-volt power supply and the reset button, and we have also added the navigation buttons that will be used in future versions of the MIDI module. What we need to do now is to test the prototype with the actual synth and with a MIDI keyboard to see if everything works as expected. However, since I don't want to make this video too long and boring, we will do this in the next episode of the series. For now, just a quick reminder for you to subscribe and to register for notifications if you haven't done so already, so you can be notified every time a new video is posted on this channel. I'll see you in the next video, and as usual, happy experiments!